Section 3.2 deals with graphs of equations. The graph of an equation is the picture that represents all the solutions or ordered pairs for this equation. So a graph represents just all the solutions, all the x and y's, all the ordered pairs that can be substituted and make that statement, that equation, true. Let's look at intercepts. X-intercepts are where the graph of the equation crosses the x-axis. Given an equation, you find your x-intercepts by setting y equal to 0 and solving for x. So in order to find your x-intercepts, you set y equal to 0 and solve for x. Y-intercepts are where the graph of your equation cross the y-axis. So your x-intercepts are where you cross the x-axis, and your y-intercepts are where you cross the y-axis. You find your y-intercepts by setting x equal to 0 and solving for y. Okay, so when we graph equations, we're going to be looking at a lot of different things. We are going to be graphing a lot of equations in section 3.6, and that's not going to be for a little while. One of the things that we're going to do is we're going to be finding the intercepts for these equations. Another thing that helps us when we are graphing equations is looking at symmetry. What kind of symmetry, if any, that our equation has. So let's look at the three different types of symmetry. The first is symmetry with respect to the y-axis. Let's look at a picture of this. So if this is our coordinate system, here's x and here's y. Something that is symmetric with respect to the y-axis looks like this. So what does this graph mean? What does that mean? Well, it means that if I fold my sheet or paper over at the y-axis, so if I fold it in half at the y-axis, the graph will line up. Means whatever exists here exists on the opposite side. Now, no, this isn't the prettiest picture, but imagine if I could fold this at that y-axis, I'd have the same graph on both sides. Okay. Well, how would I determine this algebraically? In order to determine this algebraically, if you have some equation, y equals x or 3y equals 4x or what have you, in order to figure out if you are symmetric with respect to the y-axis, you would substitute a negative x in for your x and simplify. Okay. If you end up with the same equation, I want to say with the original equation, then you're symmetric with respect to the y. And I'll just say symmetry with your y. Okay? So Algebraically, we would plug in a negative x in place of our x, and if we end up with the same thing after I simplify, then I would know, yep, I am symmetric with respect to the y-axis. Okay. Let's look at the next one. The next one is going to be symmetry with respect to the x-axis. And a graphical representation of this. X and here's your y. Look like this. If I would fold this paper over at this x-axis, the graph will line up. That's how I know that I'm symmetric with respect to the x-axis. So if I fold the paper over at the x-axis, the graph lines up. Okay. So whatever point exists here exists on the other side. In order to determine that algebraically, we would substitute a negative y in our equation for y and simplify. If we end up with the original equation, and I'm going to write EQUAT for equation, then we're going to be symmetric with respect to that x-axis. So symmetry with respect to the y just means you're a mirror image across this y-axis. Symmetry with respect to the x-axis means you're a mirror image across the x-axis. The last thing that we're going to look at is symmetry with respect to the origin. Now recall the origin is where the x-axis and the y-axis meet. Right there at 0, 0. That's what we call the origin. So here's an example of a graph that is symmetric with respect to the origin. Basically, you would figure this out graphically if you fold the paper over at x-axis. You'd fold your paper over at your x-axis, and then again at the y-axis. And your graph would line up. Okay. So imagine if I fold this graph would be down here, or this line, this red line. If I fold it again at the y, then it would be over here. So my graph would end up lining up. So any point that exists here would exist over on the other side. The way that you determine algebraically if something is symmetric with respect to the origin is you would substitute negative x in for x and negative y in for y and simplify. If you end up with your original equation, then you have symmetry with respect to the origin. Knowing what kind of symmetry you have helps you when you graph an equation, because you know that if you're symmetric with respect to the y, as long as you know what one side looks like, you'll know what the other side looks like. Same thing if you're symmetric with respect to the x-axis, as long as you know what the top looks like, you can figure out very easily what the bottom looks like. Or with the origin, as long as you know what one side, you can flip over and then over again, and you'd know what the other side looked like. So when we graph equations, and again, that we won't get to really graphing all of these functions and equations until section 3.6, symmetry is just a way of helping us determine what our graph will look like. All right. So let's just practice. What we're going to do with the next couple of examples is we're going to find the intercepts of each one of these graphs, as well as determine what kind of symmetry it has just by looking at it. We won't do it algebraically. So our first problem here, let's find our x-intercept. Our x-intercept are where we're going to cross the x-axis. Well, I cross the x-axis right here, and that point just happens to be at 0, 0. So my x-intercept is 0, 0, or I can just say x equals 0. Either one is fine. My y-intercept is where I cross my y-axis. Well, here's my y-axis. I cross it at the same point. My y-intercept here is 0, 0, or I could just say y equals 0. Now I need to figure out what kind of symmetry, if any, I have. Again, if I were to fold this paper over at this y-axis, I would realize that the left-hand side and the right-hand side would match up. Because of that, I can see that this is symmetric with respect to the y-axis. Great. Let's look at our next one. Again, let's find our intercepts first. First one I want to find is my x-intercept, where I cross my x-axis. Well, I cross my x-axis at this point. Well, that point happens to be -1, 0. So I can write -1, 0, or I can say my x-intercept is x equal -1. Now I want to look at my y-intercept. My y-intercept is, again, where I cross my y-axis. Well, here is my y-axis. I cross it here. Well, that y-intercept, that is the point 0, -1, or I can say that it's the point y equal -1. Either way works. You don't have to do both. Just choose your favorite. Well, now I need to look at symmetry. So if I fold this over right here at the x-axis, at the y-axis, would I get the same thing on both sides? No, I would not. Okay? I know that I'm not symmetric with respect to the y. Let's see if I'm symmetric with respect to the x. Remember, in order to be symmetric with respect to the x-axis, I need to fold myself here along my x, and the top and bottom would match. Well, that's not going to work either. Symmetry with respect to the origin means that this point here would exist on the other side and then exist down. Well, it doesn't. Okay? So this particular graph doesn't satisfy any of the symmetry that we talked about before, so this graph has no symmetry. Great. Let's go on to the next one. All right, let's find my x-intercept for this next one. Here's where I cross my x-axis, and that is at the point, it looks like -2, 0. So my x-intercept is -2, 0, or again, you can write x equal -2. So look at the y-intercepts. Well, I have two y-intercepts. So my y-intercepts, well, I have this point, which is 0, 2, and the bottom point, which is 0, -2. I could write my y-intercepts like that, or I could say that it's y equals, you can say -2, 2, or we could say y equals plus or minus 2. Either one is fine. And let's determine symmetry. Okay, well, if we look at this, I think it's obvious that our symmetry is with the x-axis. Well, let's see. So here's my x-axis. If I were to fold this graph over here, would this point exist on the bottom? Yes, it would. Okay, so folding the graph at that x-axis would create the same graph, or my graph would line up from the top to the bottom. So this means I'm symmetric with respect to the x-axis. Let's look at our last one. Our last one asks us again to find the x-intercept, the y-intercept, and then to also determine symmetry, if any, for the graph. Okay, well, this is where I cross my x-axis. So my x-intercept here is at 0, 0, or again, we can say x equals 0. My y-intercept, I cross the y-axis at the same spot. So my y-intercept is 0, 0, or I can say y equals 0. Now let's determine symmetry. Well, notice if I were to fold my graph over at the y-axis, so this would exist this way over here, right? So this would now come that way. Now if I were to fold over at the x, then this line would come right down and line up with what I have. So the point here exists over and down, which means that I am symmetric with respect to the origin. Great. Well, that was all of section 3.2. In section 3.2, again, we learned that graphs are picture representations of all the solutions to an equation. X-intercepts are where we cross the x-axis. Y-intercepts are where we cross the y-axis. And how to determine symmetry. And again, when we go to section 3.6 and we're graphing, we'll see then that symmetry will help us as we graph.